As the video shows, there are white lines emerging from the player's hands. These are the motion vectors we calculate when tracking the direction the player's hand is currently moving, and as you can see, they respond based on the player's motion. A major issue we came across when integrating our character model was finding the correct direction for the torso. This is as we don't directly track the torso, and so only have access to the two hands and the head. Our heuristic solution takes the view direction of the player's head and the vector from the torso to each of the hands. It then averages these vectors and uses that, with some constraints, as the direction of the torso. We added vignettes to our game to help reduce motion sickness. The user can select from 3 levels of strength.
A common problem identified through playtesting was losing sight of the other player. This was frequent after turning corners. To fix this solution, we implemented an additional render pass that draws a silhouette of the other player when they are obscured.
Across the development of our game, we went through 3 separate iterations of buildings. The first of these was a traditional block out of the city. This was done by extruding the footprint to the correct elevation and triangulating a mesh from there. This worked and gave a general identity to the city, but lacked great detail. The second method we used to enhance these block out buildings was a context-free grammars approach. This uses a context-free grammar and a parser to correctly map windows, doors, and other details onto the buildings. Whilst this worked, there was still a lot of detail lacked. Our final approach was to use an add-on for Blender called Buildify, which we could run from within Unity when pre-computing buildings. Buildify takes a 2D footprint for a building and can generate a building of the specified height. It does this by instancing individual modules like walls or doors onto a set mesh, kind of like building with Lego. We found this provided the most realistic buildings we could find, and so we generated several variations of generators to give that variety. To add realism to our game, we used a shader that projects cube maps behind the windows. This is a relatively new technique that provides a very efficient way to render interiors. To create the water in our game, we used 2 normal maps scrolling in opposing directions to one another. This provided a performant way to create realistic water as it's handled in a shader. To reconstruct the roads, we first built a network graph from the OSM data. We then merged nodes connected together in ways to make longer roads. The set of points are plotted as a series of Bezier curves so that the road curves smoothly. Finally, the ways are greedily merged together to get longer roads with less disconnects. This improvement can be seen in the transitions in the video. Our custom grass shader not only had color variation, but also vertex displacement to simulate wind. In addition to this, there were scattering parameters, including clumping, size variation, width variation, and distance variation to fake density further away from the camera. Grass also turns to face the camera to further improve density. An essential part of hiding many of our optimization shortcuts was a fog system. To do this, we reused one of our team members' old code and repurposed it for the project. This provided more sophisticated and advanced fog than the standard built into Unity, allowing for both vertical fog and horizontal fog that blended correctly into the skybox. This was essential in allowing us to use many of our optimizations. To create the particles, we used Unity's VFX graph. This gave us creative control over how the particles looked from a node-based system. An example of the particle system is the leaves and glows at the edge of the arena. Another example is the map of the UK being displayed on the holotable. This was modified from Unity demo files. To cull buildings in our game, we used an off-the-shelf solution called Instant OC. Instant OC allows for occlusion and frustum culling without the need for baking. This is because it uses a raycast method where if a building, or collider in this case, is hit by a ray, it will remain visible on the screen for a set period of time. By combining Instant OC with a process called chunking in which meshes are merged, we were able to greatly improve the performance of the game. Grass and other foliage is code on the GPU of our custom compute shaders. This allows us to check through hundreds of thousands of instances and only have to render the ones in view. Our bespoke procedural pipelines powered most of our world generation technology. They were built on top of a framework called Xnode. The pipelines gave us the flexibility to divide up our work and split the pipelines into sub-pipelines, namely pre-compute and runtime. Nodes in the pipeline handled tasks anywhere from generating buildings, calling APIs, and performing optimization operations.